Ready for a quiz? Quiz! We will definitely have one next week. Handout.
Did you see that? What? Control so hard. You guys will definitely have one next week. It's a handout.
Okay, guys. Good morning. We'll get started. A couple minutes late today. The handout is on multi-step synthesis. You should be looking at that. Cassius?
Last semester in OChem 1, for material seminars, we got extra credit if we went to like one, and I think there's one today that involves chemistry. Is chemistry related? Is that like applicable this semester too?
No extra credit. Please attend today if you'd like, yeah.
There's extra credit. You got to be in the right class.
Benzylic chemistry. We also have the handout today is multi-step synthesis. We need to look at multi-step synthesis today. Okay. We're going to look at a group bonding to the benzene ring. First thing is benzylic bromination. The benzylic carbon, which this carbon's called, first carbon bonded to the ring, we can brominate with elemental bromine and some type of light energy, H nu. And in this line reaction, we are monobrominating to give the CH2Br. This would be called a benzylic bromination, brominating the benzylic carbon. In this example, we're using, instead of bromine, we're using NBS. NBS is N-bromosuccinimide. I don't think we mentioned that in Organic 1, did we? I don't think we did. Some of you use NCS when you chlorinated sulfonamide, right? Who used NCS? Okay, the only difference is this has a bromine instead of a chlorine. So NBS is bromine. Instead of bonding to another bromine, it's bonding to an N, and this is a ring system here. So this is NBS, stands for N-bromosuccinimide. If that was an H, that would be succinimide. You can find this in your textbook. Because of the electron withdrawing, these electrons are pulled into the carbonyls, and so resonance structure, there's some partial plus here, and so this nitrogen is sort of electron withdrawing, and you can get a dipole this way, even though that's bromine. But actually, this is a radical reaction. So we can say that this is essentially source of Br radicals. When we look at the mechanism, we'll just state that. Now, some of you already recognize NBS was drawn there, right? Yeah. Okay. I don't have to write this on the board, right? In this example, this is standard benzylic bromination conditions. Benzylic carbon is brominated. It's a substitution reaction. We are replacing an H. There'll be other things to say about this in terms of comparing it to like ring bromination. Before we do that though, let's look at the mechanism. I'm going to show mechanism with regular elemental bromine. So elemental bromine is this. This bond here is fairly weak because the two atoms are like, they're both greedy and they don't like to bond to each other. With a little energy, we can get this bond to break, and that's what the light does. Light energy. It will break homolytically. Homolysis. Basically, one electron will go this way, one electron will go that way. And when we move just one electron, we use a fishhook arrow, a half arrow. Okay? So this would be moving one electron, that would be moving our standard 2 electrons. And 99% of everything we've done has been moving 2 electrons, like a lone pair or a bonding pair. We did do some radical reactions in organic 1, whenever we looked at maybe reduction of an alkyne to a transalkene with like dissolving metal reduction. That was our radical reaction. So, with the light, H nu, sometimes you see light sort of like this, as if the light's shining down on it. Okay? We create, what does this lead to?
BR
It doesn't lead to Br minus, it leads to Br with 1 electron. And actually 2 of these. Because bond's gone, this bromine has 3 lone pairs and 1 electron. That bromine has 3 lone pairs and 1 electron. They're identical, 2 of those. What's the charge of that bromine? Neutral, yes. It's a radical. It doesn't have a charge, but it also does not have an octet. Something with a single unpaired electron is called a radical. We get that from shining light on our bromine. Now, if you shine light on NBS, it will also form Br radicals. You could probably propose the same exact thing. In the end, I'm not going to do anything else with NBS other than say it can be used instead of bromine and it supplies Br radicals. We'll say why it's a better alternative. Okay, once we get a Br radical formed, this guy will abstract to hydrogen. I'll do it here since it's just lower down. We can do it there as well. There's 2 H's here. The Br radical will strip an H away. Essentially, we can say 1 electron here, 1 of these electrons comes and teams up with that. The other electron in this 2 electron bond stays on the carbon. So what does that electron movement give? Well, what stayed on the carbon?
1 electron.
1 electron. Right? That's what that arrow means. 1 electron's moving. Where's the other electron in that 2 electron bond going?
With hydrogen.
It's teaming up with the bromine electron. So the H electron teamed up with the bromine electron, and what did you produce? I mean, that's a Lewis structure for HBr. So if we balance this reaction up here, both of these, well, see here I'm using NBS. So balancing it is going to be something else. But if you balance the one up here, this is going to produce HBr. Okay, I'm going to erase this just to give us more room. You can move on your page. Okay, we produce, what do you want to call this guy? It's a radical. At what position? Yeah, we form a benzylic radical. Why do we form it there and not maybe over here?
Stable. Resonance.
Well, good answer is always, it's more stable. But then I will ask you, well, why is it more stable?
Resonance.
Resonance. Can you show resonance of that? Have we ever done resonance of radicals? Okay, I don't think we have. We can. We're using the pi bond here. Basically, if we're going to do resonance, what's the hybridization of that radical? SP 2.5? Well, you laugh, but I mean, there is such things as SP 2.5, SP 2.3, and I mean, SP whatever is nothing but what is your bond angle? You can actually calculate hybridization, and it could be SP 2.9. I mean, it's really meaningless. It really correlates to whatever the bond angle is, and bond angles don't have to always be 109.5. But this is going to be SP2. Let's do resonance first, then we can show the pi system. Right here, one electron, this electron here, this electron there, the other electron there. What does that give? What are we doing right here?
Double bond.
Yes, double bond. I'm not going to draw on the H. What's now on this carbon?
Radical.
Yeah, radical. That's it? Yes. I'll try to keep my bonds connected. I mean, you can keep going. This electron in here, one of these electrons in there too, the other electron out here, and we can get radical here, double bond there when these two electrons teamed up, and then here. And then you can show one more resonance structure. Go ahead and show the last one. Last one, electron move in here, one of these moves in here, and the other one moves out there. Radical there, pi bond here, here. So how does this look for resonance of a radical? Ultimately, what is resonance? It's really a blend of all this. Ultimately, we're saying that these p orbitals interact all the way around. But see, this right here is your benzylic radical. It's one electron. I mean, if you draw pi bonds, you can say pi bond, pi bond, pi bond. There's your benzene ring. But then this guy has a single electron. You see, it's interacting too. So all that's interacting. We can look at a hybrid individual resonance structures. Just like when we talk about carbocations, is this radical just right there on that one carbon? No, you see it's sort of spread around. And if we spread the radical nature around, then it stabilizes the radical. So, benzylic carbons are great places to form radicals. They're also great places to form carbocations, because you can stabilize them with the ring as well. So that's why we get the radical form here and not like out here with one of these non-benzylic carbons. Because if it was out here and there was an sp3 carbon between the pi systems, then there wouldn't be any resonance of the radical. Okay. How do we get the final product? I'm going to erase the resonance structures, I believe. We'll come back here.
We still have a radical BR. You got a radical.
We do have one radical BR left. So if the other one teams up with this, what does this produce?
Product.
Here's his final product. But that's not right. That's not the correct mechanism. Because we know something about the reaction that's not explained by our mechanism. You actually only have to shine the light at the very beginning, and then you can turn it off. And the reaction will keep going. Now usually in practice you don't turn the light off. But you actually can. For example, and that suggests that all you have to do is shine the light for a second, turn it off, the reaction will just keep going. Well, for a second, it did a couple of reactions, maybe 1% formed in that second. Well, how do you get the other 99% to form? Well, let me explain, because it may not be clear enough for you to see what I'm getting at. The actual mechanism, first off, before I erase these, why doesn't this quench with a bromine radical and we end up with bromine here? Because the radical has sort of all these structural characteristics. Why don't we get that from? Because it's not aromatic. Is that an aromatic ring? No. So that product's higher in energy, and thus most likely the transition state leading to that product is higher in energy than the transition state leading to this product. So, the actual mechanism is, instead of quenching with that second bromine that's out there on our board, it actually quenches with bromine. One electron here, one electron there. What are we making right here? Product. But what are we also making? We're giving product plus what? What are we making? Hold on, I need an arrow, don't I? What are we making right here, T? Yes. Your radical now we can explain why the light is only needed for a split second. The light is needed to start the process. We get this. Bromine radical takes a H. We get this. This takes a bromine from Br2 here. At this point, we don't need the light anymore. Why? Because this can take an H. Now we have a cycle. Okay? That takes an H, form this. This takes a Br from bromine. Radicals form. It takes an H. You see the cycle now? You turn the light off now. You don't need the light anymore. This is called propagation. You see, if we had taken the second Br like we did initially, how would we have done the second reaction, or for another molecule? We would have had to come back and do this again, which requires light. Instead, we showed a mechanism that does not require light, which is actually known. Couple of questions.
Would the excess bromine radicals react with each other?
Two bromine radicals react? Yeah, they would form this.
Okay.
Which may be why the light is usually kept on. Not only can two bromine radicals react to form bromine, which is not bad. I mean, you start with bromine, you would just need light to. As long as you maintain some carbon radicals, it can proceed. How would we make this product? You see that? How would we make that product? Such products are known to be formed in these reactions.
Two radicals.
Two benzylic carbon radicals coming together to make a carbon-carbon bond. If we react this with bromine and don't create bromine radicals, that would be called a termination step. Because it would terminate the cycle, and then you would have to come back and you would have to homolytically cleave your bromine again. These two coming together to make a sort of a dimer would be a termination step. Make sure you understand propagation and how this can just keep going. That's why we needed to use Br2 here and not that second Br radical. That leads to propagation. Everybody see that? Okay. NBS does also produce bromine radicals. NBS is better because NBS is a nice, stable solid that you can weigh out at the balance. Bromine is a very reactive liquid that's mostly gaseous. Would you rather weigh out a nice, stable solid at the balance or some gaseous liquid that is very toxic? Thank you. The solid. NBS is a safer alternative to bromine. If you drop a bottle of bromine, you're going to have to probably evacuate the third floor. If you drop a bottle of NBS, well, you just sweep it up. And so it's just a safer alternative. Okay, why bromine? Well, it turns out it has the correct or the good thermodynamics. We're not doing any thermodynamic calculations. Thermodynamics may give you selectivity. I think there was another question here, but
Yeah. Because it is propagated, since there's the other Br radical, could it take the other H and have a dibromo on the benzylic? Or
you certainly can. That could theoretically be a side product. Usually you can get monobromination in pretty good yield. One thing we wanted to say, but I lost it. Mike?
Yeah, what's the fate of the other radical bromine? Because I feel like it's really reactive.
Well, you could get two. You could maybe envision two cycles going. And actually, there's probably multiple cycles going because as soon as you turn the light on, you probably form a million of these gets cleaved, and so you produce 2 million bromine radicals just like that. And so you may have 2 million cycles going. But if we look at one cycle, though, then we have to understand the idea of propagation.
Okay, so this is just for the one single cycle for the propagation. Like that is just looking at one, not all of them combined.
Yeah.
Okay.
So is there certain equivalents that you need use of this?
No, it's just standard one equivalent. What's required to do this reaction?
Light.
Well, yeah. Actually, sometimes you can just heat it, and you can get your bromine radicals formed by just traditional heating. With the lights on in the lab. Is the heat doing it, or just the light from the lab doing it? You know, do it beside the window in the lab. What you don't want to do is like do it in the dark. Right? Sometimes light can be bad. For example, what if you want the bromine to brominate the ring? Is that a radical reaction or an ionic reaction? Ionic. Maybe you want to do it in the dark so it doesn't form radicals. It doesn't brominate your benzoic carbon by radical mechanism. What's going on? Y'all asking all these questions?
Is that why things are sold in dark bottles just to prevent like reactions like this?
What?
A lot of like medications, they come in like dark
Yeah,
bottles.
yeah, dark bottle, a lot of reagents are supplied in dark bottles because light will cause problems. Iodine compounds. I mean, a lot of iodine compounds are not stable. The CI bond is fairly weak if you look on your thermodynamic tables. A little bit of light, this will cleave and you'll get radicals and you can make iodine as one side product. Because two iodine radicals, once they cleave, can come together and make iodine. As someone mentioned about the bromine. Or maybe I did. That's why a lot of iodo compounds are colorless when pure, but as they age, they'll turn yellowish orange. They're forming a little bit of iodine over time. Yeah, dark bottles. You know, light can cause radical reactions. Okay, what's written up here is needed? 1 benzylic hydrogen. Okay? Because you got to extract one. If there's no benzylic hydrogen, you're not going to be doing this chemistry. Not this Roman numeral 1 or Roman numeral 2. Okay, bromine's the best. Fluorine and chlorine are just too reactive. The selectivity that we said you're going to get here at the benzylic position, if you do chlorine, it'll form radicals out here. You might say, why would it form less stable radical? Well, again, it's like water coming down the road. You ever see water go uphill? Well, what if it's a hurricane? Some might go uphill, yeah? See, chlorine and fluorine is like hurricanes. It's so fast, it's like it loses the selectivity. Iodine, on the other hand, is very lazy. A lot of this is also just thermodynamically based. If you do calculations, try to do this with iodine, it'll actually be endothermic. Doesn't mean it can't happen, but these reactions are reversible. Don't know, I was joking about the questions. Good questions. I wish we had time to discuss all these reactions in detail, but you know, that's just the nature of the beast. We have a good amount of material to cover. In review, I always ask questions outside of class. That's good. Why would you want to put a bromine there? What's it good for?
Leaving group.
You're supposed to say absolutely nothing. But none of y'all know that song. If we put a bromine there, now we have a great leaving group. Now we can do all types of chemistry. Maybe we can react it with KCN. It's one of my favorite reagents. Remember KCN in Sunshine Band? Y'all get too young. What are we going to get here? What mechanism did it just do? SN2. You want to balance this? What else is formed here? KBr. Okay, what are we doing down here? That is a carbon chain, not a T. Sterically hindered base, what does this look like? E2. E2 product. Basically, without the bromine, very little bit of you can't do any chemistry out there. But the radical bromination then sets you up to do all types of stuff. And from here, now we can do nitrile hydrolysis, which we'll do here in test 3. And then we can do alkene chemistry, and we can keep on building larger and larger molecules. Cashin?
For the first reaction, what do we do about stereochemistry?
Well, I didn't illustrate any here. This is chiral. I mean, if that was R, then the product would be S. Okay, how do we do this multi-step synthesis? I hope you all give it a try. I mentioned it last time. And I gave you a handout of some multi-step synthesis. 2 full pages of problems. Anybody get a product of this? 4 steps. Brittany, you get a product? Myron? What's the first thing do to benzene? What is this? What does that look like? Friedel Crafts what? Acylation. So number 1, do we have to worry about directing effects? No, anywhere you want, right there. That's after number 1, right? What do you call that compound? Acetophenone. Okay, what is bromine FeBr3 going to do to acetophenone? Somebody said it. That's a meta-director. And so we're going to brominate here. How do we know we're not doing benzylic bromination? There's no light, good. There's also no benzylic hydrogen. Bromine and Lewis acid, you're typically doing ring bromination by ionic mechanism. Bromine and light, typically you're doing radical, which is typically benzylic or allylic. Okay, we're up to metabromo acetophenone, 3-bromo acetophenone. What does zinc mercury with HCl do to this? What is that reaction called?
It's like a Clemmensen oxidation.
Clemmensen reduction. Deoxygenation. So now we have an alkyl group. Now NBS and light, what is that going to do? Add bromine where? Let's see, that's an ortho pair director. Oh, benzylic. Oh, okay. So right here. In place of an H. There you go. Now what if we reacted this with that there? What would that give? SN2 substitution with our alkoxide. Somebody said elimination. Possibly, but methoxide is not a sterically hindered nucleophile, so I'd probably say SN2. Usually when you want elimination, you usually will use a sterically hindered base. Unless it's tertiary, leaving groups on tertiary carbon, then it has to be elimination. Okay. Here's an example of some benzylic chemistry. This is the synthesis of anastrozole, it's a breast cancer drug. Shown here, number 2. How do they make it? Well, they start with 19, but actually probably comes from benzylic bromination, right? Probably. We'll see it again. KCN, they substitute off both bromines with nitrile groups. Then they treat this with base and make anion. That's a stable enough carbanion to make a methyl iodide. And so they attack to an SN2. They do that twice on each carbon. That's how they get the 2 methyls here and here. But let's go to the next reaction. The next reaction, what are they doing? 21 to 22. They're putting a bromine on the other benzylic carbon. What are they using?
MBS.
ABS. What is that? If you draw that Lewis structure out, that'll be benzoyl peroxide. Benzoyl peroxide. What do you use benzoyl peroxide for?
Bromination.
I thought you were going to say for a little acne or something. 10%. Another way to form radicals is to use peroxides. If you add in a peroxide, it will facilitate formation of radicals. So that's what they're doing there. Sometimes you see people use a peroxide analyte. Carbon tetrachloride is a good solvent for radical reactions because it doesn't have an H, and so it won't participate in the reaction. But there you go, they're doing a benzylic bromination. From here, they come in and do another SN2, but with this sort of aromatic anion, and these electrons kick off the bromine, and that's how they get this triazole ring bonded to the benzylic carbon, and that's the breast cancer drug. Okay, the second benzylic reaction we'll see is benzylic oxidation. If you have a benzylic carbon with at least, what do you need to have on the benzylic carbon? At least one hydrogen to do either of these reactions. If you have that, if you treat it with one of the big 3, remember the big 3 oxidants? Sodium dichromate, chromic acid. KMNO4 is the most common for benzylic oxidation, but the others will work. You'll oxidize the benzylic carbon to the carboxylic acid. So now the carbon, how many bonds to a more electronegative atom does the carbon now have? 3. Where here it had none. Highly oxidized. You also see 2 oxygens added. This mechanism we're not going to look at. It's probably radical. Instead of radical bromination, it's probably radical oxygenation. And it probably, you put 3 OHs on the carbon, or you replace every benzylic hydrogen with an OH. Is that, then you lose water. So this is not stable. We'll learn more about this during test 3 and 4. This will then lose water to give your final product. Don't really worry about the mechanism. Just giving you some details. Main thing is you have to have at least one benzylic hydrogen. If you do, you're going to get the benzoic acid. Now uniquely here, if you have a longer side chain other than one carbon, such as this example, benzylic carbon with an H, You'll also get the benzoic acid. You'll say, what happened to the other two carbons? They get chewed off and spit out as what? CO2. Each carbon becomes CO2. This can be 100 carbons long, and you'll make 100 CO2s. We're not going to look at the mechanisms, but it'll chew them all off. Does that make sense? As in terms of just an outcome, a predictive product? Again, we're not doing mechanisms.
So you said that one makes 2 CO2s then? Because it's got 3 2.
It would be 2 CO2s, because you got to have, the other two carbons have to, they can't just be disappeared.
Yeah.
They're eliminated as CO2.
Okay.
Predictive product here. Let's came in before we're going to do this ethyl group. It's got one benzylic hydrogen. It's going to chew it all off. Carboxylic acid. Is it going to react with that guy up there? No. There's no benzylic hydrogen up there. It's not going to react. Actually, reaction with KMNO4 can be used as a chemical test.
To see if it
Essentially, it tells you, do you have a benzylic hydrogen? Now, it's not going to be a visual test where you get a color change. You have to sort of isolate your product and then maybe go run an IR and then say, whoa, look at that, it looks like carboxylic acid. And the only way I was able to get a carboxylic acid is my compound must have had a benzylic A. Okay? Why is benzene highly toxic? Carcinogen. Usually it's not even used in industry anymore. Okay? Why is it carcinogen but toluene not? Because it has a methyl. That doesn't answer the question, though, does it? We all know it's because it has a methyl. Why? What about the methyl makes it less toxic? Well, the body is a lean, mean oxidizing machine. The body will also oxidize this benzoic carbon to the acid. Now, this is more polar. Also, in many places in the body, your body's basic, and this will exist as the anion. Now this has great water solubility, and it can be flushed out of the body. Where benzene typically gets in the body, and it just goes to like fatty tissue, and it just hides there. And when the aqueous blood comes by, the benzene's like, I'm just staying right here. And so it builds up in your fatty tissue, and it starts causing problems. Where toluene gets flushed out. Cause of benzylic oxidation. Toluene is a much more preferred solvent. The boiling point of toluene is about 30 degrees higher, which makes it not as convenient to remove. But still, toluene is a good and common solvent. You can buy toluene at Lowe's. You ain't going to buy benzene at Lowe's. Toluene is used in like the paint industry to dilute paints and stuff, especially for if you use oil-based paints. Okay, let's try another multi-step synthesis. Can you synthesize that compound from benzene? And I gave you a sheet today of about 8 different multi-step synthesis problems for target compounds. You can be working on those. We'll be hitting those next week some more. So, multi-step synthesis we looked at before. We're going to go backwards. Retrosynthetic arrow, we're going backwards. Let's take a group off. Let's take off the nitro group. If I had this, can I make this?
Yeah.
How would you make that? Who said you?
Would it?
Well, it would be a meta
It
director.
would. It'd be a meta director.
Ah, that's a meta director.
To put a methyl there.
So if I try to nitrate this, am I going to get that as the major product? No. It's a meta director. Well, let's go back the other way. What if I go back to nitrobenzene and then say, hey, if I start with nitrobenzene, can I put on this?
You have a CH3.
First off, we've not seen any reaction to directly put on a carboxylic acid. We'll actually see some down the road during test 3 and 4. But you don't know any reaction now. You don't know a direct way to make this. You know an indirect way. What's the indirect way to make this? First add an alkyl group, then you can oxidize the alkyl group with the benzoic acid. Anyway, what type of director is this? Yeah. So even if you could put the group on directly, would it go para to the nitro? No, not by an EAS mechanism. So how are we going to do this?
Add the nitro or the methyl one.
Well, you can add the methyl, then add the nitro, then oxidize the methyl.
Okay. Okay. Let's see what was just said. This has a precursor. And very often in synthesis with aromatics, your precursors are going to be good because, especially if they have a different directing effect than the end thing. So I'm sort of going to, now I've got it in my head after sort of doing this. Do we want to nitrate first or do we want to put an alkyl group on first? Alkyl. Because if you nitrate first, the next thing is upgoing metal. Let's make that. How would you make that?
Yeah, acylation. What's the?
I would do acylation followed by reduction. Clemenson, or you can also use Wolff-Kishner. I'll just do that to remind us of Wolff-Kishner. You need to show reagents. Wolff-Kishner is hydrazine and hydroxide. Okay, variety weight, that would give this. Why did I do 2 carbons? Because 1 carbon would have required an H here. I just like 2 carbons better. Doesn't matter, we can chew them both. We can chew the N carbon off, right? Okay, now what do you want to do? Do you want to oxidize this to the acid first or nitrate first?
Nitrate.
Nitrate, because this right here is your orthopara director. What do we nitrate with? Nitric acid, H+ catalyst. We get this. Now, plus what? Plus ortho. But when you're doing these synthesis problems, we're going to say, we're just going to purify out the other one. Okay. We don't have a reaction that just goes para. We can purify this out. Now what do we do to get final product? Now we do our KMNO4 heat to oxidize the side chain. If we had oxidized first, we would have had the acid. And if we nitrated that, it wouldn't have gone para. Please look at the sheet I gave you today and try to do something. Actually, you should be able to do the first 2, definitely. Actually, I think you should be able to do on the front side with the holes on the left, you should be able to do all 5, except maybe the one with the cyano group. The cyano group we were going to see can be put on using a diazonium reaction. That's the next in the handout. We also have the other handout I gave you. That'll be a big one next week. We'll be doing some reading about this, multi-step synthesis. Also remember there will be comprehensive spectroscopy on each test. Have a good day, guys.